Okay, good morning, good evening, good afternoon, everyone. Uh, Still people are attending. Apologies for the delay. Uh, so let's get started. Thank you for joining us today for the MICCAI Industrial Talk. And I have the pleasure today to have Dr. Ronnie Rajan, who will be speaking to us today about real-world lessons from deploying AI for population scale chest X-ray screening. Ronnie, I'll try to be brief, but I'm sure Ronnie can also speak about yourself. Dr. Ronnie Rajan is the Vice President of AI and Applied Sciences at M42, a global health organization harnessing AI technology and genomics to transform healthcare. A physician with over 8 years of clinical experience and a postgraduate degree specializing in AI and clinical data science from IIT. He has over 7 years experience bridging medicine and data science to enable the responsible adoption of AI in healthcare. At M42, he leads AI research and development across NLP, large language models, medical imaging, and genomics, advancing the translation of cutting-edge AI research into clinically meaningful application. It's a pleasure to have you, Ronnie, here today. The floor is yours.
Thank you so much, Mohammed. Absolute pleasure to be here. I'd like to thank Mohammed, the MBZ University, and also the MICCAI Society for giving me the opportunity to present here. Um, Mohammed mentioned, my talk will be on real-world lessons from deploying AI for population scale chest X-ray screening. We're going to use, I think, one of the projects that we've built and deployed here in Abu Dhabi as a case study to think about what does it take to deploy AI in clinical practice. So just to get started, I think all of us know the hype around AI, right? It always starts with these big claims that, AI is ready for fully autonomous systems that can replace doctors, outperform doctors, are ready for clinical practice, and it kind of exaggerates the hype and also exaggerates the expectation around what AI can deliver in healthcare. Um, with each new innovation trigger, I think this is a usual cycle that happens. There's a cycle of hype, followed by a reality check. When there's increased assessment of these systems and competence and evaluations, we feel like we realize that the hype it didn't live up to the expectations, and you realize that there are nuances to deployment, to integration, and to multiple aspects of delivering clinical impact that people oversee during that initial hype phase, right? There's a social trend behind this. I think this is well captured in this concept called the Gartner hype cycle. So Gartner, the consultant company, releases a prediction of what the hype around technological advancements is almost every year, and they describe this as the cycle of there being a technology trigger of a new technological advancement or invention, and then a peak of inflated expectation because of the overpromise. And then there's that row of disillusionment when you realize that things are not as great as you expected them to be. And then slowly, when you start building on things and working on those small nuances to make it work better, you go through the slope of enlightenment. And then finally, there's a plateau of productivity. And this is just a reflection of, I guess, the impact of individual overconfidence to collective hype of society. And that's just the normal psychology of human society. Now, when you specifically look at this hype cycle when it comes to AI and maybe specifically AI in healthcare, it goes through different iterations, right? So if you look around 2 years ago, there was different technologies at different phases of the hype cycle. The latest, I guess, for the 2025 cycle, you can see things like agentic AI and open source LLMs being at the top of the hype cycle, and things like radiology AI getting more into matured deployment phase when people realize what it takes to convert early research into clinical deployment and implementation. Now, not all technology goes through this exact phase of going into this plateau of productivity, right? There's a considerable portion of AI ideas that fail because they fail to translate from early research to clinical reality. And I want to base my talk about what distinguishes these systems, what is the difference between the systems that succeed and the ones that don't. Now, this is not a new thing that was, discovered, right? I'm not claiming something new here. This has been well documented in history, specifically in radiology and medical imaging, because in a way, AI in healthcare it began with, AI in radiology and AI in medical imaging, and that's why it's very well documented. And multiple papers have highlighted this gap between research and impact and what it takes to create that clinical impact. One specific paper I'd like to highlight is this one, which is integrating our AI into healthcare systems, and the fact that it's more than just the algorithm, it's more than just the model. One direct quote from there I'd like to say is this, right? So, despite the rapid growth of AI applications in healthcare, very few models have progressed into beyond retrospective development or validation, or like a POC or a demo phase, creating what is commonly called the AI chasm. Now, among the subset of models that move into RCTs and actual clinical trials, even fewer have demonstrated actual clinically meaningful benefits. And this reality is a reminder that translating AI algorithms from in silico development or research environments to real world clinical settings is still remains a challenge. Now, what is this AI chasm? So, AI chasm, you can describe it as the gap that between these two phases of the development life cycle, right? Chasm is the gap between the AI experimentation phase and the AI in production phase. It is the gap between the algorithms that seem to work in research, but somehow don't, I guess, and the AI systems that actually deliver sustained value in real clinical workflows. Most medical AI models never make it past the demo phase because they work very well in research environments but fail when deployed at scale. I think one of the earliest examples of this was the Google retinal screening tool, where it showed exaggerated performance in research settings, but when deployed across the world, even in third world countries, it failed miserably. Now, I'd like to think about my experience and talk to you about my experience or our experience at Infotone crossing this AI chasm and how to build and implement impactful AI solutions and what it takes. So I categorize most of our learned lessons into these four main buckets, right? So there's robust data foundations, there's clinically aligned development, there's extensive real world validation, and there's responsible deployment. Now, I'll just take you through these nuances in the aspect of this one case study, like I said, on the chest X-ray TB screening. Now, IRIS-TB is a model that we developed. It's AI radiology and screening TB. It's a model we developed for TB screening. Now, why TB screening? Why the context of this whole problem? I'll explain a bit by getting into what M42 is, what the company does, and one of the assets that the company operates, which is relevant for this. So just a quick 5 minutes on what the company is. So M42 was formed with the merger of two entities based in Abu Dhabi. G42 Healthcare, which is a healthcare vertical of a technology company called G42, and Mubadala Health, which is a healthcare vertical of an investment arm called Mubadala, both based in Abu Dhabi. This was formed in 2023, but over the years it's expanded more by acquisitions and mergers to beyond 26 different countries with over 480 healthcare facilities and 15 million patients, right? Now, all of M42 is divided into three major platforms: global patient care, integrated health solutions, and digital health solutions. So, under GPC, we mainly look at people, so which is mainly clinical and healthcare operations. We have healthcare facilities, hospitals, clinics, labs, focusing on renal care, diabetes, long-term care, women's and children's specialty hospitals, outpatient care clinic, diagnostics, etc. In the IHS platform, we have these population scale sequencing labs and biobanks that also operate the local National Population Genomics Program called EGP, Emirati Genome Program, with a plan to sequence over 1 million genomic sequences from local population. We also operate an environmental science lab, a clinical research organization called IROS, and all that is under the IHS platform. The third platform is the DHS. Under that, we operate the National Health Information Exchange of Abu Dhabi called Malafi. We also operate the Claims Exchange portal and multiple digital and patient platforms. Now, if you look at the individual assets, like I mentioned, under GPC, there's a lot of clinical assets, then there's labs, there's digital assets, and so on. The one asset I want to focus today is this Capital Health Screening Center. Now, Capital Health Screening Center runs population scale visa screening service for the UAE. So, for those of you who know this, all visa applicants to the UAE need to go through medical screening. So they use this medical screening not just for you know uh, acceptance of the visa application, but also to screen for specific diseases, sexually transmitted diseases, TB, things like that. So one of the tests that's taken is the chest X-ray, and this chest X-ray is taken specifically for TB screening. Now, when we look at the operations around TB screening at CHSE, we realize that there's just too much volumes, right? So I think 2 or 3 radiologists at the center look at around 2,000 scans in a day. The center alone looks at around 500,000 scans in a year. And there are multiple, I guess, visa screening facilities all around UAE, which conduct around 3 million scans annually for specifically for TB screening. But in all these scans, because it's a population scale TB screening and not a patient level screening, 99% of these cases have zero findings. They're just coming there because they're mandated to as part of the visa application process. And less than 5% have some findings that may be relevant to TB, and less than 0.5% are actually tested positive for TB. So as you can see, there's a very heavy manual burden that the radiologists take to screen for those very minor cases. So if you look at the current workflow, this is what it looks like, right? So you have 99% normal cases and 1% abnormal cases going in for manual review. And if the manual review, the radiologist marks it as normal, it passes visa screening. And if it's marked as abnormal, it goes through 2 additional blind reviews. Now, because this is a workload problem, we realize when we talk to the clinicians, we realize that it doesn't need support in terms of TB diagnosis, because radiologists are good at TB diagnosis. What it needs is to automate the normal reporting so that it kind of reduces the workload of the radiologist. So what we redefine this workflow as is using the AI model as an initial screen so that it can screen out all the cases that have zero or no significant findings, and only send cases with some significant findings for the radiologist review. And in a sense, when you think about this workflow, it reduces the workloads without actually impacting the workflow. The actual workflow of the radiologist remains the same as before. Now, this safe automation of normal reporting can happen only if you can ensure that the automated scans have a very, very low false negative rate. Now, if you look at this as a classification task, these radiologists classify these X-rays into 3 classes. One is normal with no findings, one is abnormal but not TB, so non-TB abnormalities, and then there's TB associated findings. And then the TB associated, the ones that are suspected to have TB associated findings go through confirmatory molecular testing for TB, and then the ones who are actually tested positive get their visas rejected. So that's the entire process, right? So to replicate that radiologist thought process, we need to classify this as a multi-class classification. But to replicate or to enable this workflow of removing the monomers out of the entire work list, you need to again binarize that multi-class classification into a binary class classification of normal versus abnormal. And that's what we did. So what we did is looked into the historic data. We collected over 10 years of historic data from CHSE from uh, 2011 to 2021. We got around, I guess, 2.5 million scans, and then we excluded the non-PA view. So PA view is the posterior anterior view, the view from the front, right? So we excluded that, and also any older visits for the same patient. So any multiple visit or repeat visits are excluded. And finally, we had development test of 1.6 or 1.68 million scans. Then we had a test set isolated with a temporal time split. So the test set was for cases that came in from January 2022 to January 2024 with over 1 million cases, even after the exclusion criteria. Um, yeah, so obviously there's a huge class imbalance like we talked about before, right? So we adopted some techniques to address that class imbalance. We did batch class balancing to improve the minority representation. We did some data augmentations. We did a sampling ratio of 1:3 for abnormal to normal, where the normal is the sample. We also did some histogram equalization and sorts, and then we trained the model. Now, I want to go back to the main point over here, right? What did we do different over here? Now, I want to focus, I guess, this discussion around clinically aligned performance metrics. Now, it has been recorded in multiple studies that many of these assessments hyper focus on very few performance metrics like ROC and accuracy. But it's also important to think about what are other metrics that really align with the clinical problem, the workflow, and the impact of errors. Right? It must be easily explained to the clinician so that they trust the output, and also because of their trust in the output, there's increased adoption of the system itself. So that's why, with that in mind, what we chose, the main two metrics we chose to optimize, are around two tracks, right? How do you improve the safety of the system? Safety of the system means I should make sure that the system doesn't miss any positive findings. Specifically, it should try to never miss a TB case. So that is the measure of safety, which we decided as the false negative rate, and then a measure or a metric of operational impact. So that is measured by workload reduction. So that is what percentage of scans can we automate reporting off, thereby reducing the overall workload of the radiologist. So these are the two metrics we decide to optimize, right? Now, in the false negative rate, there's also a subclass where you have to be very sure that you try to minimize at the most the TB specific false negative rate. Because if you think about the clinical operations or the impact of errors in that specific metric, what happens is you have a patient coming in for not a patient, but you have a person coming in for his visa screening, and they use this mandate as a way to opportunistically screen for TB. Um, if you have an actual TB case that's missed by the model, which skips manual review by the radiologist and gets automatically reported as normal in the system, you have the chance of an actual TB case bypassing the screening, which is an actual public health concern, and the failure of the screening itself, right? So for us, the TB specific false negative rate is the most important safety metric. So the trick is to find that threshold, to find that point where you have the maximum operational impact, which means the highest workload reduction possible, while maintaining the highest safety, which means the lowest TBFNR possible. And this is the idea that I want to bring of clinically aligned performance metrics instead of just trying to optimize or maximize things like ROC and accuracy alone. We did some more threshold selection tricks to try to think of multiple thresholds that can be accepted by the clinic, and they can choose a threshold in a way to decide what is priority for them. So, for example, while making sure the FNR is lower than the doctor's, the radiologist FNR, can we opt for two thresholds where you have the choice of having a more safer setting or a more optimal setting with increased workloads? Um, so if you think about these two concepts, there's two thresholds, right? So there's a safe setting, which is starting point, which is a very low threshold with a high safety. So high safety corresponds to around 0.33 false negative rate, and a low efficiency gain, I would say low compared to the other one. So the low is still at a 40% workload reduction. And the optimal setting, which is the ideal point where operations should come to once there is trust and adoption of the system, where there is a low threshold, but I mean, not very high safety, still a high safety, which is lesser than the radiologist false negative rate at 1.75, but a considerable efficiency gain with over 80% workload reduction. So that's why this choosing the threshold, depending on what your clinical workflow is, matters a lot. And then we also did some calibration because that is critical in healthcare models to increase interpretability, right? So we did spine calibration to fit on the validation set, and this increased, the performance a bit more, as you can see here. Now, and the point I want to talk about is hidden stratification. So we ran these models, we tested it. I'll get to the validation in a bit, but I wanted to touch on this point before I get to the main results of the validation study. So in a three-class classification problem, and I said that we classified this as normal, abnormal, not TB, and TB cases. We realized that the model was missing out on a lot of subgroup of TB cases. So we had a high TB FNR rate, and we wanted to understand what that means, right? And that's when we realized this concept of hidden stratification. Obviously, we worked with the radiologists a lot to identify these cases, to go and annotate and find these errors in all the false negative that we found. And what we realized is There's this paper around hidden stratification that talks about in your minority class, there exists hidden stratifications, which means there exists multiple subgroups with easy to difficult range of annotation or class separation capability, which means that within this TB class, there exists some subgroups where the model finds it more difficult to classify them as TB. So if you look at that in the clinical setting, doctors typically spend a lot of time assessing the difficult cases. So that's why if they make a mistake, they're bound to make mistake on atypical cases, but they never miss out on, critical cases. For example, if they're trying to detect cancer and there's a highly aggressive type of cancer, I'm saying this from personal experience, right? Doctors spend a lot of their, study time focusing on these aggressive type of cancers, the rare type of cancers that should never be missed, and that's why their accuracy on detecting these aggressive type is always higher. They might miss out on others. So, for example, if you have an AI system and a doctor, and if you have similar performance metrics around the same data set, it's a high chance that doctors will never miss those aggressive types. So the high-risk subtype performance of doctors would be much higher than the AI model, clearly because of the lower representation of that subclass in the data, the AI model is bound to miss that at a higher rate than radiologists. And this is the concept of hidden stratification. This is exactly what we found in our work as well. So when you look at these findings of, I guess, TB in chest X-rays, you see that the top row have very typical features like lymphadenopathy, which is enlargement of lymph nodes. Pleural effusion is the presence of liquid between the pleura, which is the covering of the lung. Consolidation is the solidification of or mass formation around the lung area, and cavitation is a solid area with, I guess, um, fluid or airy space within it. So these top row features are very prominent in active TB cases. But if you look at old TB cases, so TB is a disease that once it affects you, there's a chance that it lays dormant. You have some fibrosis, which is scarred healing of the tissues, which stays over time, and there's a chance to recur again. Right? And that's why in old TB cases, you have a very different presentation when you compare to active TB cases. So the bottom line over here that you see of findings like atypical fibrosis, calcification, which is calcium deposition of the areas that was initially impacted by TB, and also collapse of lung. These are atypical findings that are not present in active TB cases. Now, this is a small minority of old TB cases that have these atypical findings. There's also a section of old TB cases with no findings at all. So it very closely matches to normal TB cases. So that's exactly what we also saw. And we were able to find this because of our interactions and discussions with the radiologists. So we realized that the subgroup within the TB class that we were missing out were mostly old TB cases. And we need to think about a change in our training methodology to make the model, learn these features of old TB a bit better. And that's why what we did is we changed this into a four-class classification where we have normal, abnormal, not TB, active TB, and also old TB, and then binarized into normal versus abnormal as usual. Now, this immediately increased the performance, and then we ran the validation study on the internal set, probably the world's largest validation study to test the performance on over 1 million chest X-rays over 2 years of data from 2022 to 24. Um, and we found that the TBFNR is quite low, so 0.07. So that is the main metric of focus, like I mentioned, right? So 0.07 corresponds to two missed cases in a million scans over, I guess, 200 suspected cases and over 20 positive cases, if I'm not mistaken. We also did external validation of this, again, focusing on the TBFNR and realized that for other external public data sets like CheckSpurt, Chest IU, Pad Chest, and TB 11K, our model achieved a 0% TBFNR, which means it didn't miss a single case of TB. And the important thing is to compare with the confirmed test. So, like I mentioned, all the scans that are suspected to have TB findings then go for confirmatory molecular testing. So, we also evaluated our model's scores on the confirmed case of TB. So, like I mentioned, there's around 2,780 referred cases where there was radiologically suspected TB, and out of which 257 were confirmed to be TB positive, right? Now, we can confidently say that our model showed a strong confidence in all the confirmed TB cases, with all the prediction scores clustering around 0.99, and the lowest score of a positive tested case was around 0.8, which was much higher than the threshold. So this shows like a good class separation, which increases, I guess, confidence, not just for us, but also for the clinicians who need to use this. And increased confidence and increased trust is what leads to increased adoption of the system. And the important aspect is bias analysis. It's a well-studied field right now over the past 2, 3 years, where we realize that there's a lot of bias in historical healthcare delivery and in health systems. There's systemic bias. And what we need to do is make sure that we understand these intricacies of biases or difference in disparity in performance of these different subgroups. So we did bias assessment mainly focused around the same metrics for gender, age, WHO regions, country income group, and HIV status. Again, these are recommended subgroups by the WHO guidelines. Um, One thing I must admit is that the WHO has extensive guidelines around TB screening and implementation of AI systems and computer-aided diagnosis systems for TB screening, because this was one of the first use cases that was explored using AI, right? And that's why most of these guidelines or implementation techniques are recommended by the WHO themselves. The last thing we did was, like I mentioned, we did find two false negatives, which is like TB annotated cases, which were diagnosed as not normal, right? So two in the safe setting and three in the optimal setting. So we reviewed all the false negatives, not just the TB false negatives, but all abnormality false negatives by the radiologists, and we manually sat with them and reviewed all of this, right? And what we realized is what they said is all three cases happened to be an annotation error. The first case was a normal scan with some unrelated obesity, which does not indicate TB. And they said that it is possibly a technical or human error. The second case, again, was obesity and fibrosis that was not indicating TB. And again, they said that this could be, there's no sign of active TB, and this should be abnormal, not TB, and definitely not a TB case. The last case was that of interstitial lung disease. Now, there are multiple studies that claim that interstitial lung disease has findings that are very, very similar to TB, and it's very commonly misdiagnosed as actively widespread TB. But all three cases on confirmatory testing was confirmed to be negative, which means all three cases were not TB. Now, when you think about this from the implementation standpoint, what this means is our model recognized errors that the radiologists got wrong in the first place, right? So implementation of a system like this actually would improve safety in a way that it also not just improves safety in with respect to low false negative rate, but also reduces cost in a way that on implementation of such a system, you would not need to do unnecessary confirmatory testing for cases that are not obviously TB. Now, on correction of these three cases, we realized that our TB FNR rate is actually 0%, which means we validated this model on over 1 million scans with zero missed cases of TB. And we have a lower false negative rate of other abnormalities, even lower than radiologists. We also have high class separation, so high ROC, and the potential to automate up to 80% of radiologist workloads. So the impact of this would mean that instead of looking at 2,000 cases in a day, the two radiologists at CHSC today can look at just 400. And despite that heavy automation, we still managed to have a false negative rate lower than current radiologist rate, and also maintain a 0% TBFNR, which improves the safety of the whole system. But beyond safety, it reduces the workload of the radiologist. So I guess the burden is lesser, the retention is better, their the scope of screening itself increases, because right now they have more time to actually screen for things beyond TB. So instead of spending their whole day looking at 99% normal cases, they can look at cases that have some findings. They can potentially find or opportunistically screen for other conditions, refer them to specialists. The scope of the entire screening program itself goes beyond just TB, which is a very welcome change. Like I mentioned, I think most of this is guided by WHO, and which is another important step. Right? So clinicians always come to us and ask, like, okay, is this something you are leading? Is this something a technology firm just came up with the idea without clinical backing, or is there some clinical evidence behind all this? And like I said, it was easier for us because there exists guidelines from the WHO directly, specifically for TB screening. Um, which indicates that CAD can be used as an alternative, not just assistant, but alternative to human interpretation for chest X-ray, specifically for TB screening and triaging. The only thing is that they expect to have a target product profile of over 90% sensitivity and over 70% specificity, which our model does. And the thing they have is complete, very comprehensive guidelines on how to integrate the CAD into the screening process. So this whole idea of using that as an initial screen came from the WHO recommendations. This whole idea of threshold calibration, how to design the study, how many patients to take in, the outcomes to be interested in, how to calculate costs, everything came from guidelines of WHO. So when we show the doctors that we have followed clinical guidelines by world um, global regulatory bodies, that kind of increases the trust in the system further, thereby increasing adoption. So in the end, it's all about what are the steps you can take to increase adoption, because that is how you scale your deployment. And the way to increase trust and adoption is doing this three-phase deployment. This is another thing that was mentioned in one of the studies, where you have a three-phase deployment where you take them through a retrospective analysis of the past data. And most of, I guess, POCs and demos get stuck here, right? You get access to historic data, you train a model, you prove that the model works, and that's about it. The difficult part comes in the next phases, right? So phase two is all about integration. So if you can, integrate with the current workflow in a way that is seamlessly integrated without any impact on the current workflow, um, uh, without any automation of reporting, which means there's no risk per se until the clinicians and the operating team gives the go ahead, right? So you're able to assess real world impact analysis without actually changing anything in the workflow. It's just a shadow deployment where both the AI system and the doctors annotate the same image, and you can continue to have that assessment. So, like I mentioned, I think the retrospective analysis was done over 2 years of data. Prospective analysis has been going on for almost another 1.5 years now. And by Jan, we are aiming to do the final deployment, which is phase three, where we actually start automating reporting. So once you automate reporting, the workflow changes, which means the workload of the radiologist reduces. And that's when you should implement performance audits and periodic updates and getting, regulatory clearances and things like that. So all that comes in phase three. Now, integration is another part. So to make it seamless, what we did is instead of doing it ourselves, we use this orchestration platform, which is an FDA 510(k) cleared orchestration platform that takes care of PACS and EHR integration, that does the AI model orchestration, and also enables audit system, prospective AI monitoring comparison with other, say, commercial solutions. You're also able to do prospective studies and things like that on this platform, which makes auditing easier. Again, coming back to the same point of implementing whatever it takes to improve trust of the clinical operations team in the system and thereby adoption. And the thing that really increases trust is the compliance. So there's this whole push, at least locally, to have local models prioritized, and the fact that it's compliant by WHO guidelines and has an FDA-approved orchestration platform, and it's also approved by the local Abu Dhabi Public Health Center Visa Screening Committee, and it's compliant also by the DOH TB screening standard. So I think compliance to regulatory standards is another thing which is highly critical, which influences adoption by a lot. So as long as you can show that you're compliant by these standards and guidelines, there's going to be increased trust right away from the very beginning. And the thing is, real world validation with a peer reviewed study. Obviously, we did that. We had published the study at NPJ Digital Medicine, and we showed that we are able to achieve a 0% TBFNR rate with validation over 1 million scans, and enable an 80% reduction of radiologist workloads. They're also compliant by standards, and there is a clear impact on this. Now, next steps I would say is, like I mentioned, by Jan, if you start automating, the next steps would be thinking about what is the real world clinical impact post automation and post deployment. You also think about what is the economic impact, what is the impact on the radiologist workload, which means is there a way that we can scale operations without improving cost? Is there a way to optimize the cost without, implementing some other tools? There's a lot of nuances that we can test even in the phase three. Those are for next steps. Now, just to summarize, I want to come back to my original slide, right? So, what does it take to build and implement such impactful AI solutions? Right, it goes beyond just traditional performance assessment. You think about nuances around robust data foundations. You need to have clinically aligned development. You need to extensively validate in the real world and responsible deployment. So, looking into this a bit deeper, data foundations means you need to have representative data sets. You need to handle the class imbalance. You need to think about reliable annotations. You need to, mitigate the hidden stratification, which is a real problem, especially in medical imaging. You need to have enough diversity in the data sets that's representative of the population you're going to implement it in. You need to have robust annotation standards and expert consensus on the annotations. Clinically aligned development includes clinically aligned performance metrics, not just using the standard metrics, but thinking about what really matters to the clinicians and to the clinical operations team. And kind of showing the story of what your model can achieve in that light. Also, alignment with regulatory and clinical guidelines that the clinical team approves of helps a lot. Thresholding strategies that are aligned with the clinical workflow, intensive subgroup analysis to ensure bias assessment and mitigation. Technical robustness assessment, which is again a long-term, performance assessment, and having a human in the loop design where you include the clinicians in all your decision making, right? So in our process, we were working with the clinicians in extensive workshops to identify what kind of use case we should target. So we went for automation of normal reports instead of TB diagnostic system. We included them in the assessment of the false negatives and the false positives. We included them in the reannotation of scans and restructuring of the entire modeling process. They were involved throughout. Even now, we continue to work with them, and having that human in the loop from the beginning kind of again builds the trust in the system and thereby adoption. Extensive real world validation is extremely important beyond just retrospective validation that's typically done in these demo environments. Prospective validation is important. Things like what we did around shadow deployment with real integration into the systems, real world integration, but a seamless integration in a way that their workflow does not get impacted a lot. But because one thing I can tell you doctors hate is any change in their workflows. They stick to systems that work for them because of the trust they have in those systems, and any change of their workflow is not very well taken. So if you can implement or integrate into their workflow in a seamless way that doesn't really change their operations, then they'll accept it better. Multi-site robustness assessment, as looking at variability of hardware and protocols. So multi-site assessment becomes important. Post-deployment validation, like I said, also becomes important. So where you look into the real-world clinical impact post, say things like automation, and the economic impact. So is this really worth it? So one of the experiments we also ran is with the advent of, say, foundation models. We trained a foundation model as well to see if transformer-based, models can have a better performance. What we realized is yes, the performance increases, but at a higher cost because these are bigger models that require, I guess, more cost for deployment. So then it comes down to the same point of if it's worth that additional improvement for this additional cost, right? So the economic aspect of things also matters a lot. Last point is responsible deployment, which means you have to make sure the system is safe and all that. Obviously, you have to make sure the ethics is followed, the data privacy is followed, seamless integration into the existing clinical workflows there, and minimal change to the radiologist workflows. User trust and adoption is one thing I kept repeating all throughout, I guess, because that is probably the most important of all. Regulatory alignment with, say, existing standards of the regulators locally and globally, responsible AI, aspects of things, change management to make sure that if there's any changes to the workflow, it's managed properly, it's adopted properly. And again, making sure human is in the loop for taking these decisions. And there's also an audit process in place for, security and things. Yeah, this is all I have for today. You can scan this code for access to our Hugging Face page. There's some more models that we do. I think we work a bit in research of LLMs, imaging, genomics a bit. Happy to also connect on LinkedIn to discuss further.
Thank you very much, Ronnie. That's exciting talk. We have quite a few questions. I probably can start if I don't mind. I can start with question in my mind.
Okay.
Uh, really interesting work and amazing results that you achieved. Do you think there
Thank
might
you.
be a little issue in terms of data? Because your training set is, your testing was on data from 22 to 24, which is probably after
Yeah.
COVID. Probably after the
Yeah.
training set is like 10 years of data that, in healthcare system, these machines, chest X-ray machines, keep on changing
Yeah.
or software gets updated. So do you think that it may be able to generalize for future data sets? What's your thought on that? And also consider COVID. We didn't have COVID
Yeah.
before in your training set, and maybe you had COVID patients in your testing set.
Yeah, absolutely. A very good question, Mohammed. So the way we look at it is, first of all, because of this temporal split, yes, there will be, you know, differences in the data that's used to train the data and to test the data, right? In a way, this is a test of the generalizability of the model itself, because we also do subgroup analysis across not just demographic features of the patient, but also systems, right? So we also looked at
Mm,
subgroup analysis of different systems, like imaging protocols and the systems used in these centers. And we also did external public data set validation. And in all these cases, we realized that the performance was uniform. So there is good generalizability. And the fact is that because we've I guess, modeled the problem in a way that it's not more about diagnostic, but more about abnormality versus normal detection. Uh, the presence of COVID, the presence of any condition, all gets grouped into that abnormal class, right? So in
mm,
the end, COVID, it's more about not diagnosing a condition, but more about detecting features of disease. And if you look into radiological findings, right, most of these diseases have very common patterns, right? So COVID in the end has consolidation features, has
mm,
features that are there in other conditions as well. It's just that the spread or the location or the localization might be different depending on the disease. So COVID might have more in posterior and lower lobes, whereas a TB will have in the upper lobes, but the features are the same, right? So that's why when you binarize all these abnormal outputs into one abnormal class, I don't really think it matters, because in the end, what you're looking for is features and not
yeah,
diagnosis. So that's why framing that question or framing the whole problem matters a lot.
makes sense. So let's take some of the questions.
Yeah.
First one is, I think you answered that, but let's say it again. What is your negative and false positive of TB screening, and how could you reduce them? I think you mentioned there's two different type of false negatives that you used. So
Yes,
I'll let you
there
answer.
was. Yeah, there was the all abnormality false negative rate, which is around I think 1.57. So we were trying to keep it lower than the radiologist, and that's how we chose the thresholds. The TB specific one, after the reannotations of those three scans, right now stands at 0%.
And false positive, I don't think you care too much about it
Yes,
because
actually, that's exactly the point, right? So false positive, I mean, there is a sensitivity specificity trade-off, right? For this, I guess, problem at hand, which is automation of normal reporting, we want to push for more false positives, because we want to diagnose anything that resembles some kind of abnormalities and push them
yeah,
towards manual review. Because false positives, for me at least, for this problem, is a good thing, right? You'll have the radiologist review more of these scans manually, which means that there's a potential to increase the scope of the screening. So the whole trick is to manage the workload reduction and the false negative rate. As a byproduct, if false positives are increased, that's good news for us.
okay. Next question is, did you test these models in any other screening center? If so, how
Yes.
did you perform the calibration?
Yes, I think we tested it in the screening center again in Abu Dhabi. It's called Reem Hospital that does the same thing. We're also in talks with other screening centers in other regions of UAE. Very early talks right now, but the only one we completed was the one in Abu Dhabi. We got very similar outputs. We still maintained around the same workload reduction for a 0% TBFNR. Those, at least we only ran the POC, which was, I guess, the retrospective analysis phase. So we did not change the thresholds. Now, the plan was that in phase two, we'll prospectively deploy in their systems and assess it over probably 6 months of time, and then we can make a decision on that, right? So, but so far, what we did was just retrospective analysis, just assessing on the model as is with the same thresholds.
Yeah, maybe if I also want to add, since I am also in Abu Dhabi, the data is coming from population from all over the world because
Yes, yes,
90% of the population from more than 190 different countries. So if you're going to
yeah,
looking for a diverse data, the most diverse data in the world is probably here in the UAE. Okay,
absolutely,
next
yes.
next question is how do you convince doctors to use the tool or the product?
It's just more than 3 years of effort, right, Mohammed? So we started working with them early 2023, where we defined the problem. And like I said, all the steps that we took were to increase trust in the system to make sure they adopt it in the end, right? So because that's what matters. That's what the talk was about,
Mm.
right? So every single step where they were in the loop, they were with us in defining the statement, a problem statement, in defining what their pain points are, what we want them to work on. So when we went in with the idea that we'll help you diagnose TB. And they are the ones who said, no, no, I don't need a model's help in diagnosing TB, but we have a lot of workloads. Can you do something about that? So just them being involved in that decision-making process itself increased the trust. And it was just years and years, I guess, continuous years of working with them that increased that trust and hence the adoption. And then, like I said, having these regulatory clearances, talking to the right people, integrations, making sure it's seamless, all of this, the more they trust the system, I think they are ready to adopt.
Sounds good. So next question is, how do you calculate a false negative rate for radiologist? I guess means that how do
Yes.
you calculate agreement with the radiologist as well?
Yeah, yeah. Agreement is one way. Like I mentioned in that workflow, right? So each the normal gets automatically approved, and the abnormals goes through two blinds. So
No, no.
one part is a disagreement between or agreement or disagreement rate between radiologists, and the part is this also goes through an audit. So 3% of scans which are detected as normal by the first radiologist that doesn't go through the blind reviews goes through an audit process every single day. So we also looked at the agreement or disagreement there as well. So that's how we calculated the overall false negative rate between radiologists.
Okay. Uh, Question is currently the focus is on TB and you achieve great result. What other pathological condition would you like to monitor closely in future?
Yeah, I think this is a very good question. So this again depends on the clinical pain points, right? So what I'd like to focus on is we need to work with the radiologist to understand what is of value, right? And yes, it's interesting to work on good, exciting problems, but it should also be clinically relevant. So if I talk
Yes.
about CHSE in particular, CHSE is the visa screening operation unit of M42, which is my company. Now, they use this as a population screening tool for visa screening, but one important aspect for them is to do opportunistic screening, right? So
Mm.
the way we are trying to implement opportunistic screening right now is just to say, okay, we'll reduce your workload so you have more time spent that you can spend on the abnormal scans. So naturally, you will, or the radiologist will do the opportunistic screening. Now, as phase two, they also want to look at can these systems recommend or diagnose multiple conditions? Now, we need to work with them to identify what those conditions are, if there are annotations in the system, or if there are public data sets around that. But some interesting ideas around, say, looking for a cardiac score, looking at chest X-rays, detecting diabetes. There is some research also around this, right? So those kind of opportunistic screening is something that's very interesting for radiologists here. Some things which are interesting from a research point of view, for example, lung nodules and things like that, are not, surprisingly, not that interesting for a radiologist, at least in our center, because from their perspective, I think. Um, even with early detection of lung nodules, there's not a lot of, I guess, impact because a lot of them end up being false positive in the end without a lot of clinical impact. So for them, some use cases are interesting, some are not. So it involves us working with them actively to identify what those use cases are.
Okay. So next question is, how do you see leveraging transformer architecture helping the model?
Yes, I think I did touch upon this a bit. So
I think you did, yeah.
we tried the foundation models track a bit. We did achieve better performance. So we were able to maintain the same 0% TB FNR. I think the same around the same all abnormality FNR as well, with a higher workload reduction, right? So instead of 80% for the optimal threshold, we were able to achieve a 90% workload reduction. But in the end, there's many aspects to this, right? So with the efficient net architecture, we are able to deploy it on a CPU setup locally, on-prem in their servers, which is, I think, financially costs around 10,000 dirhams, which is around, I guess, $2,700 a year. Now, pushing this to a transformer architecture might increase the price, the cost of deployment, and we'll have to reassess all the impact on the clinical assessment, the impact on FNR, the impact on, do this whole prospective validation all over again. So the practical point comes, is it worth the change? Is that 10% increase in performance worth the change? And that aspect is what we're trying to do is reduce the workload so that they look at more scans, that they can uh, find these, I mean, conduct opportunistic screening and find new conditions, right? So if you automate more, which means lesser scans go to them, right? So then this is really worth the effort where they want to be doing more opportunistic screening. So it's a more philosophical question, I guess.
And one question was about the model. Like, did you perform, is there a specific foundation model you tried?
Uh, I I think, I mean, we trained our own foundation model. So it's called CX Former. It's on Hugging Face. So if you scan this, you can get that as
Yeah.
well. I think it is on Hugging Face. So we trained our
Okay.
own model using the same data.
Okay. Next question is interesting. Did you consider per demographic thresholds, or did you find a uniform threshold to work across all demographics?
Yeah, so I do not think we tried demographic-based thresholds. We just used a uniform threshold. Like, I mean, our focus was on TBFNR, right? So because it was zero from the start, we didn't go to fine-tune it a lot. Maybe at the all abnormality FNR, there could be some fine-tuning done. But again, uh, the more important aspect is the TB one.
Okay. A last question. I think you answered it during your presentation, but I'll ask, how would you test the model during the deployment phase with the chances of TB positive cases being present is low? How would you
Sorry, I
test
didn't
that?
get that. Can you come again?
It's more about like, how would you test the model at deployment stage if you know that the chances of
Okay, okay.
positives is very small?
Yeah, I think again, I mean, it's we through the platform, through the orchestration platform, we're also implementing this audit system, right? So the current audit system looks at 3% of normal annotations of the radiologist. We're also implementing another audit specific around the model. So we have to make sure that because anything annotated as normal by the model bypasses manual screening, we make sure to audit all the high scores among the normal annotations. So that's how we try to make sure that we don't miss out any of these TB or even non-TB specific findings through that audit trail. And the way we make sure, I mean, I guess in the end it all comes down to auditing the system.
Hmm. That's good. I think that's all the questions. Thank you very much for the exciting talk.
Okay.
I learned a lot today about the work of our next door neighbor, and
Yes.
I look forward to talking to you in future. And thank you very much for your time. Thank you for people who attended
Absolute
today.
pleasure, Mohammed. Thank you.
Thank you, Ronnie. See you everyone soon for another industrial talk. It won't be in December. Next time will be first week of January. So stay tuned. Thank you, Ronnie. Have a good evening.
Thank you. Thank you so much. Take care,
Thank
everyone.
you. Bye bye. Thank you, Diana. Bye
Goodbye.
bye.